Hello, space explorers! Caroline here, and today we're going to make a model of our solar system. I've asked Mia to help us. Mia, let's assume the sun is all the way to the left. That's our starting point. Mercury is the closest planet to the sun, so let's decide where to place it. Wait, Mia, where are you going? Oh, Mia says that Mercury is 36 million miles away from the sun, so she's headed out to space with her Mercury model. That wasn't what I meant when I said a model of the solar system. Whoops. I may have forgotten to mention to Mia that we're making a scale model of the solar system, so it won't be nearly as big as the real one. Well, we may have lost our helper for today since Mia's now traveling through space, but I'll walk you through how to build a solar system model that fits in your house. Or at least in your yard. No spacesuits required. But we will be required to do math today. Math is one of the most important tools for astronomers because it's very reliable at predicting and explaining the universe. So grab a calculator and let's get started. Have you ever built a model of a cell or maybe of an atom? In these cases, models were used to represent a very small object in a way that was bigger, so we could see and understand it. Will the same be true of a solar system model? We definitely don't need to make it any bigger. Instead, we'll make it smaller than the real one, but with the same goal, being able to see and understand it better. You may have some experience already with scale models if you've ever played with die-cast toy cars, such as Matchbox cars or Hot Wheels. Take a look at this vintage die-cast model of a Volga gas. How much smaller do you think it is than an actual Volga gas? Die-cast cars such as these commonly have a scale factor of 1/64th, meaning the model is 64 times smaller than the actual car. So we could define a scale factor as a value that tells us how much bigger or smaller the objects in our model are than the actual objects they represent. This means that for Matchbox cars, every part of the car is 64 times smaller than the corresponding part on the real car. And this is what we mean when we say that a model or representation is made to scale, that every part of it has the same scale factor. Of course, as we'll see today, we sometimes do need different scale factors for different factors of a model, like the size of the objects versus the distance between them. Can you think of any reasons why? Keep this possibility in mind as we go through the lab. Let's start by scaling down the diameters of the planets in our model, since I certainly can't carry around a full-size version of any of them. Earth's diameter is around 7,900 miles. My Earth model that I cut out measures 1.5 centimeters. How big should Jupiter be if it's to scale? Jupiter's actual diameter is around 87,000 miles. Let's find out how many times bigger than Earth Jupiter's diameter is. 87,000 divided by 7,900 equals approximately 11. So Jupiter has a diameter that is around 11 times bigger than Earth's diameter. This means that the Jupiter model should be 11 times wider than the Earth model. See if you can make the calculation. How many centimeters across is my Jupiter model? "11 times 1.5 centimeters is 16.5 centimeters. So this is the width of my scaled Jupiter model. As you work through your lab, you'll find the diameters of the other planets using this same method. But how do the model diameters compare to the actual diameters? Our model Jupiter is around 850 million times smaller than the actual size of Jupiter. This is our scale factor. What must be true about all of the other planets in our model for this to be a scale model? They will all need to be 850 million times smaller. We found the scale factor for our planet models, but Mia already had a correctly scaled Mercury model in her hand when she zoomed off into space. The problem was that she didn't understand how to properly scale its distance from the sun. If we use the same scale factor for distance and scale down the distances from the sun by a factor of 850 million, will that work? Mia would be 850 million times closer than wherever she is headed in space. That has to be an improvement, right? Let's see. 36 million miles divided by 850 million. Mia would only have to go about 4/100ths of a mile, or about 223 feet. Wow, sorry, Mia, that would have been so much easier. What about the outer planets? Neptune is 2.8 billion miles from the sun. Scaled down, that's, still over 3 miles away. Remember my earlier warning about how size and distance might need different scale factors? This is why. Suddenly, this model isn't looking so practical after all. We'd rather keep our planet models in sight and not have them scattered across town such that we have to drive between them. Don't worry. The instructions in your lab will help you make a more reasonable scale for our planetary distances. Before you get started building your model, there's one more unit we need to learn. When Mia zoomed off to place Mercury into our solar system model, do you remember how far away she said it was from the sun? Around 36 million miles. And we just learned that Neptune is nearly 2.8 billion miles from the sun. Dealing with large numbers becomes a common theme in astronomy. In a previous lesson, we learned about light years, a unit that scientists use to measure the large distances between stars and galaxies. Remember that a light year is equal to about 6 trillion miles. Could we use light years to measure distances in our solar system? Pause the video for a moment and record some thoughts in your notes as to whether this would be a helpful idea or not. We certainly could measure these distances in light years, but saying that Earth is 0.0000158 light years from the sun is no more convenient than saying that it's 93 million miles from the sun. We end up with the opposite problem, values that are much too small to work with easily. Light years are great for measuring the vast distances between stars, but for distances within our own solar system, not helpful at all. What's the solution? Another unit. Scientists invented the astronomical unit for this purpose. I know, they're not winning any awards for creativity with the name of this one, but you'll often see it abbreviated as AU. So what is an AU? Well, it's equal to about 93 million miles. Does that value sound familiar? Didn't we just say that Earth is 93 million miles from the sun? So 1 AU is equal to Earth's average distance from the sun, also known as its orbital distance. We can measure other planets' orbital distances in AUs as well. Let's take Mercury, for example, orbiting at 36 million miles compared to Earth's 93 million miles. How many AU is Mercury from the sun? Pause the video, grab your calculator, and see if you can figure out how to make a ratio of these values. To find Mercury's orbital distance in AUs, we need to divide its orbital distance in miles by Earth's orbital distance. 36 million miles divided by 93 million miles equals 0.3978, which we'll round to 0.4. So Mercury is 0.4 AU from the sun. Or we could think of Mercury as being 40% of the Earth's distance from the sun. What about Mars? It orbits at a distance of 142 million miles from the sun. Pause the video and calculate its distance in AUs. 142 million miles divided by 93 million miles equals around 1.5 AUs, which means that Mars is 1.5 times farther from the sun than Earth is. You'll find the distances of the other planets and AUs as you do your lab to build the scale model. Well, I'm going to see if Mia is back from her trip and suggest that she scale this mission down for the rest of the model. You'll find all the help you need to make your own solar system model in the lesson activities, so grab some scissors and measuring tools and start building. Next time, we'll wrap up this unit and start preparing for your unit assessment. Until then, keep your eyes open for all the wonders of our universe.
Hey, hey.